Bismillahirrahmanirrahim. Welcome to the channel. My name is Asim Amjad, and in this video lecture we start our topic related to elastic beam bending. The learning outcome is to derive the strain curvature relationship for pure beam bending. And so we will start with a simply spotted beam, and we will apply moment to either end so that this beam is in pure bending. It's under flexure with a constant bending moment, and there's no shear forces being applied, and so we made some assumption. The first assumption is that our beam is symmetric about the xy plane or the plane of bending. Let me give you some example. The first example is a stair or a rectangular beam where if you draw a line down the x and y plane, you can see that on the left hand and the right hand side it would be a symmetric. The same thing with this cross section, they are symmetric about the xy plane, and again if I draw a line down the xy plane, I can see that this is a symmetric cross section, and this is a typical I-beam that's symmetric about the plane of bending. And we also made the assumption that plane section remain plane. I have drawn a marker on this beam. The plane section, you can see that I bend this beam, that those plane remain in plane. They don't wrap in and out of the plane, and so there's no twisting. There's also no buckling, and we will talk more about buckling in our future lecture. And we are going to be working with small deflections. And so here's my beam with constant bending moment applied. Let's now look at a little differential element. So we will take a slice out of that beam and we will go ahead and bend it. And so what I have got here is I have got my constant moment applied on either side, and here's my original position of the beam, and an exaggerated position once it bent. And it's bent through an angle d theta, and when I bend this beam with constant moment on either side, you can see that the top above the dash line, that section of the beam is in compression. Those that compress together, and at the bottom of the beam is in tension. But there is a line or a surface or an axis right along the center where the beam neither contracts or extends, so it's not in compression or tension, and we call that the neutral surface. But there is a line or a surface or an axis right along the center where the beam neither contract or extend, so it's not in compression or tension, and we call that the neutral surface, and I have identified the neutral surface here on my diagram as well. And we say that the radius of curvature is from point where we interested the curvature down to the neutral surface, and so the curvature is equal to kappa. It's given the symbol k, and the dx is the arc length, and it's equal to the rho, the radius of the d theta, and so kappa then is equal to 1 over rho, or you can say the radius of curvature, or if I substitute in dx over d theta, and it's equal to d theta over dx. And now I want to look at an axis a little above the neutral surface. It's up a distance y, and again by an arc length the radius is rho, the radius of curvature minus y, so that rho minus y times d theta. That give us the length of that line, that black line. And so I can substitute it for d theta is for a relationship we derive in above, that is d theta over d x. So after rearranging this equation, the d theta is equal to dx over rho. So we simply plug in over there, and then after solving this term we come up with this equation, that is dx minus y over rho times dx. And for now let's recall back. The normal strain is defined as the elongation per unit length, or you can say the change in length over the original length. And so here, for my example of this differential element, we see that the original length of my black line before it deformed would be dx, but then I subtract y over rho dx, so it's shortened by a distance negative y over the dx. And so that's my delta, and therefore my strain curvature relationship say that epsilon in the x direction is that change in length which is minus y over dx over its original length of black line, which is dx. And so that's the strain curvature relationship. I can cancel dx in the numerator and the denominator, and I end up with this relationship. And so we know that 1 over rho is kappa, the curvature, and so I can express it either way. Or we see now that strain is proportional to the curvature and it varies linearly with the distance y from the neutral axis. Either above or below, we are going to get more and more strain, and that strain is proportional to the curvature of the beam. Sign convention is the same as we used before. If it is in tension, then it elongate that positive, and here we took y being above the neutral axis, so we were in compression and we say that the strain was negative, and this is independent of the material. Note that there are strain in the y and z direction due to the Poisson effect, as we discussed in our previous video lecture related to fundamental of stress, strain and axial loading, but there's no stresses because the beam is free to deform laterally. Therefore, pure bending in beam produce uniaxial stresses. We will look stresses on my next video lecture, and I will see you then.